Welcome everyone. Welcome to this meeting. This should be the third meeting on the dependence of random variables and conditional distributions. It may be that today's session will be the most complicated one. That is, the kind of issues that we will discuss today will be maybe complicated, maybe paradoxical. I have one paradox that I want to talk about, something that people don't quite appreciate about conditional distributions if you have continuous random variables. Hopefully I will be able to explain everything properly regarding that paradox. And as for the agenda, well, the last time we talked about joint distributions, and we did talk about discretely distributed random variables. So joint, marginal, and conditional distributions for discretely distributed random variables. We did talk also about the Bayes theorem to some extent. I may want to say a couple more things about the Bayes theorem. We will see how it goes. And then it will be some new content. Previously, I used the term independence to some extent, and I did not really provide a definition for that. So I would like to provide a definition of independence, although not in full generality. The full general definition of independence can be constructed analogously to what we will discuss. Then some technical concepts, so covariance and correlation. So this is probably something that you have heard about, but not everyone actually has thought very deeply about these things. So I will have some questions, and I hope you will be able to provide answers regarding the properties of covariance and correlation. Then we should talk about this paradox related to conditional probabilities in the case of continuously distributed random variables. This is kind of to warn you that things may not be actually as easy as it may seem. That is, if you think about discretely distributed random variables, conditional distributions are not a big deal. You can define them quite easily. When you have continuously distributed random variables, it's a bit more tricky. So we will see this paradox. Then we should talk about the joint, marginal, and conditional distributions for continuously distributed random variables. And finally, I would like to also provide some discussion of conditional distributions from a measure theoretic perspective. So this will be actually kind of math heavy. I hope it will be understandable, but of course, if you are not really interested in all of these advanced mathematical concepts, it's okay if you just understand conditional distributions at the level of our discussion that we will have for the discretely distributed random variables and continuously distributed random variables. It's going to be a lot, so probably this session will be longer than the previous sessions. I will try to do well on time, but let's see how it goes. I should provide some reminder of what we had the last time. I may want to remind you of joint distributions of random variables. This was a definition that was general. It was for arbitrary random variables, and we wanted to define a joint distribution for some vector x of k random variables. So we would have k random variables, we would organize them as a vector, and then if you evaluate the value of this vector for some specific outcome omega, you would be evaluating these individual components, these individual random variables at this particular outcome omega. And then the joint distribution of these variables x, that was a function that would take different sets as arguments. So this set B, for example, and the set B, it's some region in k-dimensional space, some region in Rk. it has to satisfy some technical condition. It has to belong to this Borel sigma field associated with the k-dimensional space of real numbers. So yeah, intuitively, it has to be a well-behaved set. But if you have this well-behaved set, then the functional value of the distribution of x would be defined as the probability that x belongs to B. And we would define it using the probability measure P that we would have for our sample space, or as part of our probability space. We would look up all of the possible values of omega for which x belongs to B. And then, yeah, we take the probability measure of that. So, yeah, this is very much analogous to what we had for scalar random variables, so like single component random variables. And yeah, let me see. So a question, what does Px mean? Does it mean probability of B? And yeah, so thanks for the question. Definitely something I should make clear in here. If I have this P with subscript x, it corresponds to the distribution of the random variable x. And if we apply this to some set capital B, we are really asking for the probability that x belongs to capital B. That is, you have some k-dimensional space in which you can have different values of x. And within this k-dimensional space, you have this region capital B. It has to be a well-behaved region. And then you would like to ask, what is the chance that x is going to really fall into this region B? That's going to be the distribution of x applied to B. And how do we define it, or like which value do we assign here? It is going to be the probability measure of the set of all possible omegas, all possible outcomes omega, such that x applied to omega belongs to B. That is, to define the probability that x belongs to capital B, we look up all of the different outcomes that are consistent with that, and we look up the probability measure of that set of outcomes. So yeah, definitely there's a big distinction between Px and P. Px is the distribution of x, whereas P is the probability measure. All right, so I see this is clear. Any other questions about this? So this was our general definition. And then we talked about conditional distributions for discretely distributed random variables. I reorganized the notes a little bit, and I added some more discussion that will be actually useful for us when we go from discrete to continuous. So some brief reminder, so this is without changes, the joint PMF, the joint probability mass function, would be simply a specification of probabilities. When I wrote these definitions, I actually just wrote it assuming that the vector capital X has only two components. I didn't want to really clutter the notation, but you can probably easily take these definitions and generalize them to k different components of X. Here we have k equal to 2. So these are the individual probabilities of possible pairs x1, x2. And yeah, these are probabilities that may be non-zero, and only for x's belonging to some set D, you will have the possibility of non-zero values. That is, yeah, we had some examples before with a roll of a die and a coin flip and so on. So only some combinations, x1 and x2, they will be possible. They will belong to this set capital D. And for other values of x1, x2, we just say that this probability mass function is equal to 0. D1 was the set of possible x1s, D2 was the set of possible x2s, and then the probability of x, the distribution of x applied to B, was this probability that x belongs to B, and we could express it using the probability mass function. We will have something analogous also in the case of continuous variables. we defined marginal probability mass functions basically by reducing this two-dimensional problem to one-dimensional problem. If someone asks you for the probability of some particular value of x1, you would take the original joint probability mass function and you would sum it up over all possible values of x2, keeping the value x1 at the specified value. Yeah, similarly for x2. And then we had conditional probability mass functions. They were defined as ratios. And I'm going to remind you of that, and then I will have some additional comment, because this additional comment will help us generalize this concept also to the case of continuous random variables. So what was the definition? Well, we would say that this conditional distribution of x1 given x2, this conditional probability mass function, it's going to be a ratio. In the numerator, we would have the joint probability mass function. In the denominator, we will have this marginal probability mass function. And of course, this is going to make sense only for values of x2 that have a positive probability. Otherwise, you would be dividing by 0. So we leave this undefined when the value of x2 has literally 0 probability. And yeah, if you think about it, it would be kind of hard to generalize. It would be hard to generalize this to continuous random variables if we really started with these kind of ratios, right? Because if you have continuously distributed random variable, then any individual value of x2 would have 0 probability. And to kind of prepare ourselves for the definition that we will have in the case of continuous random variables, I provided a little bit more discussion in here. Specifically, this formula that I wrote here is something that I did not include the last time. So let's take a look at that. If someone asks you what is the probability that x belongs to capital B, and you are supposed to express it using conditional distributions, then you can write it in the following way. You can basically decompose the contributions into like changing values of x1 and changing values of x2. So yeah, we are going to have here a double sum, one sum over x2, one sum over x1. Then in the sum, we will have an indicator function. So this one is an indicator function for the point x belonging to capital B. So if this belongs, it's going to be equal to 1. Otherwise, it's going to be equal to 0. I guess that's understandable. We really want to know the probability of capital B. And then instead of having the joint probability mass function in there, we can have actually two factors in here. So we can have the conditional distribution and we can have the marginal distribution. We can have the conditional probability mass function and the marginal probability mass function. Now, why does this work? Well, so if you just take this equation here and you multiply both sides by the denominator, then you will see that the probability mass function is actually a product of this conditional probability mass function and the marginal probability mass function. So that's what shows up here. And yeah, in some sense, it's kind of simple rewriting of the probability. But this actually gives us some clue how we could potentially generalize these concepts of conditional distributions if we have continuous random variables. And that's because in this formula, there's no division, right? We are not dividing by anything that could potentially be equal to 0. So this formula in here is actually something that will generalize to continuous distributions. So this is just some more comment on something we already had the last time. And I think I may want to really briefly mention also the relation to the law of total probability. I think you mentioned the law of total probability the last time. So basically, the kind of formula that you see here is related to the law of total probability, which says that you can decompose the probability of some event C as, you can write it as the following sum. If these sets Fn correspond to some countably, either finite or countably infinite decomposition of the outcome space. So I don't really want to spend some time on it, so I'll just leave this here. But yeah, the idea is that you could split the outcome space into individual events Fn, and you would have finitely many or countably infinitely many Fn's, meaning that you should be able to order them into a sequence. And if you have that, then the probability of some event C will be the sum of probabilities that correspond to the intersection of C and Fn. So this is the chance that C and Fn happens simultaneously. It's a quite different notation from what I had here, but it's pretty much related. I just wanted to mention this for clarity, since previously we mentioned this law of total probability. And so I'm getting a question about this notation in here. What do I mean by this symbol? So this was a symbol for union, meaning that the right-hand side is the union of F1, F2, F3, and so on, potentially all the way to infinity. So it's like a finite or countable union of these different sets Fn. You can basically split the sample space into some regions. As long as the regions add up, then things will work. And I should say that these Fn's here, they are supposed to be distinct. So you should not have an overlap between F1 and F2, for example. All right, so thanks for the question. By the way, if any of the notation is unclear, then let me know. Previously we talked about this example of rain and lightning, and I think I also connected it to the Bayes theorem. So probably I shouldn't remind you of that, because that's something that we finished. But I may want to comment a little bit more on the Bayes theorem. I think we didn't have that much time to talk about it. I hope I will not be repeating myself, but just quickly a reminder about the Bayes theorem. So one way of writing this was a definition of conditional distribution for events. I did not actually emphasize it the last time, but note that this kind of definition of conditional distribution is actually consistent with the definition of conditional distribution that we had for discrete random variables. So for example, you can have an indicator function for event A1 and indicator function of event A2, then the conditional distributions you would get for the random variables would be consistent with these conditional distributions for events. So just wanted to comment on it briefly. And we had this Bayes theorem, which would express the conditional distribution of A1 given A2 in terms of conditional distribution of A2 given A1. And I'm not sure how much I actually said the last time about the intuition, but briefly, the Bayes theorem basically allows you to think about updating your beliefs about the probability of a certain event you would have some prior probability P of A1. And then if you see A2 happening, you would have this posterior probability. It's going to differ by this particular factor in here. And yeah, just for clarity, I wanted to mention here like examples. Although now that I think about it, I think I did mention it. So just very briefly, you would have a very small change in your beliefs about the probability of A2 if this kind of update factor is close to 1. And a simple example would be A1 corresponding to someone speaking English, A2 being vegetarian. So probably this ratio is of order 1. And yeah, you can have a situation where you will have this update factor very big. So a simple example would be A2, the presence of smoke, and A1, the presence of fire. So usually you don't see smoke, but given fire, you actually are quite likely to see smoke. So in that case, this update ratio is very large. And then yeah, finally, you can have a very small ratio. So A1 corresponding to a person having the flu, and A2, the same person just having finished the marathon. So in this case, the update factor would be very small because it's quite unlikely that someone would actually run a marathon while having the flu. So these are some like real life examples, but of course you would like to apply the Bayes theorem to some research context or scientific context. So in that case, you will be studying some phenomenon of interest A1, and you would have some database evidence A2. Yeah, maybe we talked about it, but hopefully this was an okay reminder. And yeah, as for the things that we have not discussed explicitly, I would like to provide here a definition of independence, at least a very simple definition of independence. You can have more sophisticated definitions. Even though I used the term independent previously at some intuitive level, I did not really talk about it explicitly. So explicitly, what would it mean that we have events A and B that are independent? Well, it would mean that the probabilities are going to factorize. So the probability of A and B simultaneously happening is the probability of A times probability of B, and say A happening and B not happening, the probability of that would be a product of probability of A and probability of B not happening, and so on and so on. So probably you understand this at some intuitive level. I want it to be explicit, but yeah, if you want to have some more sophisticated definition, you can definitely do that. And you would introduce this concept of sub-sigma fields. And again, the probabilities need to factorize in that case. If people are interested in this more general definition, then I would be happy to include it in the notes. Although, yeah, hopefully it's intuitive enough. Okay, questions. Question: why are we multiplying the two probabilities when they are independent? And yeah, it's actually simple. So let's say that you have one roll of a die and you have a coin flip. So then let's say event A corresponds to getting number 4 for the roll of a die. Event B corresponds to getting heads for your coin flip. So if these are independent, if you just do it completely separately, then the probability of getting number 4 for the roll of the die and also getting heads for the coin flip, the probability of that is going to be 1 over 12, which is this P of A, that's 1 over 6, and P of B, that's 1/2, assuming that the coin and the die are fair. So it's like a simple calculation of this type. Maybe the notation here is a little bit complicated, but yeah, I'm pretty sure people here have been thinking about these kind of settings. And yeah, another question, to check for independence, should we be checking all those equalities or checking one of them is fine? So you don't have to check literally all of them. So you can have an inequality, or sorry, you can have an equality, you can have an equality that's implied by the others. That is, if you satisfy, say, the first three, then the fourth one follows. But yeah, so it's not enough to just check one of these. Yeah, thanks for the question. So this is independence of events, and you can also talk about independence of random variables. So that would be discussed here. It's actually pretty similar. And in that case, you would say that, well, I wrote it here for discretely distributed random variables. So this will be independent if the probability of x equals some specific value and simultaneously y equal to some specific value is the probability of this particular value of x times the probability of this particular value of y. Maybe the notation I used here is not perfect. I should have actually expressed the arguments here as sets, but hopefully you get the idea. So again, the probability in here is going to factorize. The probability of some specific x and some specific y is the product of the probability of this x times the probability of this y. And yeah, again, you can make this more general using this concept of sub-sigma fields. If people are interested, I would be happy to include that in the notes. So that's something that hopefully is not terribly confusing. And then I have here a discussion of covariance and correlation. So these things can be confusing. I will see how you respond to my questions that I will have about that. So I will go through this relatively quickly, but please slow me down if things are unclear. And then, yeah, hopefully we will get to this paradox relatively soon, which is actually something pretty confusing. So as for covariance, it's not terribly complicated. Yeah, we already discussed the concept of variance. And yeah, what was the definition of variance? So you would have one random variable, capital X. So here I'm thinking of a scalar random variable. And the variance of X, that would be X minus the mean of X squared. And then you take the expected value of that. We had a long discussion of these different moments of distributions. So this is the second central moment of the distribution of X. And if you want to make it a little bit longer, if you want to make this even more explicit, instead of the square, we can write a product of two sets of parentheses. So this would be the variance of X, and writing it in this longer way will actually give us a motivation for the definition of covariance. But before that, I should also remind you that the variance could be written in a different way. You could say simpler way. The variance of X is going to be the expected value of X squared minus the mean of X squared. If you want to write the mean of X more explicitly, you can say it's the expected value of X, but yeah, you can just call it mu X in here. Now, for these formulas to make sense, of course, the expectations need to exist. So we will be assuming here that the expected value of X exists, and yeah, also the second moment exists. But yeah, this was just for the concept of variance. Yeah, it's a measure of how much the variable X varies. And now we should also think about covariance, which is a measure of how X and Y vary together. It's actually relatively simple. So you would take this definition of variance, and in one of the parentheses, one of the sets of parentheses, you would replace x by y. Or, well, I guess I should be looking at this, this equation right here. So this is the definition of covariance. If you want to have the other notation for the mean, yeah, here we have expected value of x, and this is the expected value of y. As for an alternative expression that would be analogous to what we have here, yeah, you can actually relatively quickly derive an expression like what I have here. So the covariance of x and y is going to be the expected value of the product x and y, from which we subtract the expected value of x times the expected value of y. Very analogous to what we had here. As for the derivation, I didn't include it here in the notes, but you should be able to derive it pretty quickly using the exact same method that we used the last time. If people are interested, please let me know. I would be happy to include it also in the notes here. Yeah, question, how do we compute the expected value of x squared? So I'll say this one. Or how do we compute this expected value of x times y? Well, you have to consider the distributions that you have. And so, for example, if you had a discrete random variable, capital X, you would consider the individual values that are possible, the values of x. You would square them, you would multiply them by the probability mass function, and you would sum it all up. So we had some discussion of this in the case of the shapes and moments of distributions. So yeah, we had some detailed discussion of that a couple of sessions earlier. And yeah, if these are continuous, then you would need to use integrals and so on. I may want to create some more exercises related to this so that this is completely clear. All right, so this is the concept of covariance. I didn't show you any picture, but I have some pictures in here. And okay, I'm getting one more question. So if the set includes -1 and +1, should we compute the expected value of 1 and 1? And yeah, so if you have, say, a variable x that corresponds to a coin flip and you associate it -1 with tails and +1 with heads, then indeed this x squared would be equal to 1 in both cases. And then you would take this the expected value of that. So you would get 1 in that particular case. That's exactly right. So the sign of the variable is going to cancel in this case. Yeah, as for some pictures, so what would a sample drawn from a distribution with a positive covariance look like? This is some random sample that I generated. Yeah, the point is that you see in the picture when the value of x, that's on the horizontal axis, is large, the values of y plotted on the vertical axis, these values also tend to be large. For x greater than the mean, y is also quite likely to be greater than the mean, and vice versa. When x is below the mean, y is also quite likely below the mean. So yeah, you see kind of this positive trend in here. So that's positive covariance. Of course, the distributions can be much more complicated. It doesn't have to be like this simple cloud that I just drew or that I just showed you. It can be more complicated, but the main idea is definitely valid, that when y tends to be above mean simultaneously with x being above mean, then you will probably get a positive covariance. Now, for negative covariance, of course, it will be the other way around. You see some negative trend in here. And yeah, the last picture, this was generated using a distribution. that has 0 covariance. So it's a sample. If you calculate the sample covariance, then of course it's not going to be literally 0. So that's why I wrote here negligible covariance. But yeah, you don't see any particular trend in here. Now, these pictures actually can be a little bit misleading because I just drew some simple cloud in here. It can become more complicated. Anyway, this is covariance. And yeah, any questions about the concept of covariance? Then let's get to correlation. So correlation is actually defined simply using the covariance and also the concept of variance. Yeah, you can think of correlation as being some kind of rescaled version of covariance. It's a ratio. In the numerator, we will have the covariance of x and y. In the denominator, we will have the square root of variance of x times the square root of variance of y. And of course, you may remember that the square root of variance has a name, and it's called the standard deviation. So really, the denominator in here is the standard deviation of x times the standard deviation of y. Now, using inequalities, you can show that this correlation always needs to be in this particular range, -1 to 1. The lowest correlation you can have is going to be -1. The highest correlation that you can have is going to be +1. And these are the formulas, and I have some questions in here for clarification. Let's take a look. So the first question is, does 0 correlation imply independence? Do you have answers? So if you have variable y and variable x and variable y, and they have literally 0 correlation, it doesn't mean they're independent. And yeah, looks like the answers are no. Okay, great. Yeah, that's the correct answer. But I may also want to check here this particular comment. Oh yeah, this is actually a very good question. Are there other measures of association besides correlation and covariance? I mean, is there a definition of a measure of association to which any other computations qualify? Yeah, that's a great question, and I do have actually a mention of that in my answer in here. So let's take a look at that. You can definitely think about something more sophisticated than correlation or covariance. But first, yeah, sometimes I get the answer from people that this is a correct statement, that 0 correlation implies independence. And yeah, for clarification, I have an example in here. Well, I didn't create a picture, but hopefully you can imagine what I have in mind. Let's say that you have variable capital X, and it follows the standard normal distribution with 0 mean and variance 1. And let's say y is equal to x squared. Then if you go ahead and you calculate the correlation of x and y in this case, you get 0. Basically, the positive part exactly cancels the negative part. So the correlation is 0 in here, but definitely x and y are not independent. They are actually kind of perfectly dependent. The value of y is deterministically given by the value of x. And yeah, so a question, what's the interpretation of correlation? Yeah, that's a good question. So let me go back here to the pictures. Oh, sorry. Where is it? So I have these pictures here that are for covariance, right? And imagine that you have the exact same picture, but you change the variable x. Maybe you scale it up by a factor of 2. Then, of course, the different points, they will be shifted. So instead of this point here, you will have point twice as far. So rescaling the variable x or rescaling the variable of y is going to have an effect on the covariance. The covariance is not going to be independent of this rescaling. And for that reason, you may want to think about correlation, because correlation is not going to change if you change x by a certain factor or if you change y by a certain factor. It's kind of analogous to our discussion of these normalized moments. So in our discussion of moments of distributions, we talked about the normalized version of the moments, and the idea there was, again, that rescaling the random variables is not going to change the result. So covariance, it's good to know it, but you should understand it's going to change when you rescale the variables. Correlation is some kind of version of covariance that is going to be independent of this. And of course, it's useful, right? If you perform a linear transformation of variable x, you don't want some concept of dependence to change. Maybe I shouldn't say dependence, but you may want to have something that's going to be invariant to those kind of changes, and correlation will satisfy that. And another question. So how can we find the association between two correlated variables if the correlation is 0? And I think here you mean two variables that are not independent but have 0 correlation. Well, it's actually related to the other comment we had previously. I need to get to that. But if you want to investigate the relationships here, you can create a plot, right? So that would be kind of the simplest thing. If you have two variables, you may want to create the scatter plot. And maybe you will see some particular pattern. Maybe you will see a pattern like this. And you may judge that x and y are not independent. Or you could try to calculate the mean value of y conditional on x belonging to some particular range. So if x and y are not independent, chances are that the mean value of y is going to depend on where you look at the distribution, where you look at the values of x. And so on. But like this comment and also a previous comment is related to something that I definitely wanted to mention. And let me get there. You say there may be nonlinear relationship. Exactly. And as for some concept that will capture the non-independence of variables, even if we have something nonlinear, that would be mutual information. It's something that I included in the answer in here. And so there's the concept of mutual information of x and y. You may need to be careful about how you define it, so maybe you need to regularize it properly. But if x and y depend on each other, if they are not independent, then you will find this mutual information positive. If there's no relationship, this mutual information is going to be 0 for the random variables. So as a measure of dependence, the mutual information is definitely like a deeper or more sophisticated than correlation. Now, I should also comment here on popular usage of the term correlation. And it's, unfortunately, if you look at some articles, maybe in newspapers or maybe even in the scientific literature, people confuse the concept of dependence and correlation. and they would say there's zero correlation between X and Y, when in fact they mean independence, and that's actually pretty bad. So be aware of that. Please use the right terminology. All right, so this is regarding my question 1 in here. And another comment, I guess we can also check rank-based correlations for nonlinear relationships. I like Spearman's correlation. Yeah, definitely. You can compute a lot of different statistics. So the correlation or covariance, that's just the simplest one in here. Then, question number 2. Does independence imply zero correlation? What would you say? Okay, great. Yeah, so I'm getting positive answers, and that's right. So if the variables are independent, then they will have zero correlation. And a third question, if X and Y are linearly dependent and both have non-zero variance, is the correlation equal to 1? So that's my third question in here. But before that, let me answer this one. I'm getting a question. What is the main difference between correlation and covariance? And I would say it's just scaling, right? So you would take the covariance, you would rescale it using the values of the standard deviations, and that's it. But otherwise, yeah, these concepts are roughly supposed to capture the same kind of phenomenon in here. But back to my question. What would you say? If X and Y are linearly dependent, meaning that one of them is a linear function of the other one, and both of them have non-zero variance, so that the correlation can potentially be defined, is the correlation equal to 1? And I'm getting answers either yes, or it could also be -1. Exactly, yeah, right. So I agree with that. Now, this was kind of a trick question. If you have a linear dependence, then there are two possible values. You can have 1 or you can have -1, as long as the correlation exists. All right, so these are the concepts of covariance and correlation. And unfortunately, I'm not doing very well on time. So let's get maybe to the most confusing thing right here at this moment. And I hope you will be able to stay a little bit longer. And what is my question here? Let's say that you have some distribution on a semicircle. So imagine a semicircle like this. And I tell you there will be points on the semicircle completely uniformly distributed. Uniform distribution on the semicircle. If you calculate the density of these points, then the density is 2/π. And so far it seems kind of simple, right? And I have a point C in here, that's the center of the semicircle. I have point capital T, that's the top of the circle. And you see this line in here, the line connecting C to T. And my question is, if you take this original distribution that was completely uniform on this semicircle, what would be the implied conditional distribution if I tell you that the point actually lies on this line CT? And to be even more specific, what is going to be the mean height? So how do I measure height? I guess you can measure the height as the distance from C. So for example, this point in here will have this height. So for this conditional distribution, what do you think would be the average height? Yeah, do we have opinions? So usually people have an opinion. Okay, so yeah, so the radius of this semicircle was supposed to be 1, and yeah, somehow I'm not getting the right guesses in here. So usually when people make a guess about the mean value of this height, they give me 2 specific values, and yeah. So I see one of them. So one of the answers that I'm getting is 1/2. So you basically imagine that the conditional distribution is completely uniform on this line, and then if it's completely uniform, then the height is going to be on average 1/2. So that's one possible answer, and let me show you the other possible answer, and let me provide the reasoning for them. And yeah, we should also make sense of this, because there are 2 reasonable answers in here. So that will be the paradox. So I have some visualization. So let me get to the visualization. As for the rationale for the answer 1/2, you can think of the line here as being a limit of regions like this. I'm going to change this a bit. I'm going to make this relatively thick. So this green region in here would be some part of the semicircle. You can consider the conditional distribution of the different points when you condition on them belonging to this green region. Make it big, but you can also consider the limit. So if you make this smaller and smaller and smaller, it basically becomes the line. And when this region is very thin, it basically looks like a rectangle. And you will get essentially a uniform distribution on a rectangle. Yeah, in that case, the average height is going to be 1/2. So the average height would be here. But there's another way of thinking about it. You can also think of it as a limit of wedges. So you can have a wedge like this, and as you change the angle, it's going to get smaller and smaller and smaller. Eventually, in the limit, it's going to become the line. But if you have some wedge of a finite angle in here, it's going to look more or less like a triangle if the angle is relatively small. And then you can ask for the center of mass of this triangle. And the center of mass of the triangle will be like 1/3 from the top and 2/3 from the bottom. So in that case, you could say that the average height is 2/3. And I want to argue that both of these arguments here are actually equally natural. It's natural to think of it this way. It's natural to think of it in terms of the wedges. And hopefully you see the paradox, right? So I provided 2 arguments for 2 different values, but they are not equal to each other. And then we need to ask what is wrong. So was I formulating something in a sloppy way? Was I imprecise? And so let's think about that. Hopefully you will be able to stay here for the rest of the discussion. But in case you have to leave, in the rest of the session, we are going to discuss this problem of this paradox and provide some resolution and also some measure theoretic view of conditional distributions. All right, so one question here is how did the question turn out to be the question of the average height? That's how I formulated it initially. So I said, let's condition on the event where the point that we selected, or like the point that we observed, is on this line, right? So I wanted to think about the conditional distribution And then I wanted to know what is the mean of the conditional distribution. And I provided two different ways of thinking about the conditional distribution, or what it could potentially mean. We got different answers, and that's a paradox, and we should talk about it. And there's some questions about the previous recordings. Thanks for sharing the link here. Yeah, let's think about the paradox. So this is something that I just talked about. If you think of the line as being a limit of these rectangular-like regions, you get a 1/2. If you think of this as a limit of the wedges, you get 2/3. And I have a resolution here that I want to present to you, but maybe I can ask you right now, what do you think? So what was actually wrong in the original formulation of my original question? Is there something that I did in a sloppy way? Or is there something that we should definitely avoid when talking about conditional distributions? All right, so maybe I should provide the answer in here. Yeah, the main point is that if you ask for, let me see. So the comment says the area should be 1 always. If we integrate this probability measure over the yellow semicircle, it is supposed to be 1. But the problem is actually something else. So the problem with my original question was that I asked you to condition on an event that has 0 probability. If you have this uniform distribution in 2 dimensions, then if you calculate the probability of being literally somewhere on this line, the probability is 0. It's something that you can integrate over different positions of the line, but if you insist on having just one line in here, the probability of that is 0 because the line is actually infinitely thin. Definitely that's something that we did not allow in the case of discrete distributions, and in general we just should not condition on events that have 0 probability. We can do some other conditioning, but I need to be careful about how I formulate it. The response here, yes, but we can integrate. We use probability density. Right. So we can definitely think about a decomposition of all of this sample space in here into vertical lines. We can integrate that, but we have to be actually very specific about how we are going to do the integration. I'm going to go over the notes carefully in here, but to actually summarize the argument, the point is that you are not allowed to condition on events that have 0 probability. However, you will be allowed to condition on specific values of specific variables, specific random variables. What do I mean by that? One way of thinking about this semicircle is using a coordinate system that involves directions x and y. So you will have coordinate x right here, you will have coordinate y right here. So the usual Cartesian coordinates. And if you have that kind of specification in mind, you may condition on the exact value of the variable x, and that will be pretty closely related to this kind of reasoning that we had using the areas that look like rectangles. But you can also condition differently. You can condition on other coordinates. So if you have a particular point in here, let's say this one, you can think of it as being parameterized by the distance from the center of the semicircle. So yeah, you would specify the length in here. You can call it a little r. And you can also specify the angle in here. So I'm going to call that angle phi. If you have this kind of specification of the different coordinates, so these are going to be random variables r and phi, then you can condition on a specific value of phi. If you condition on phi being equal to 0, then it's really going to correspond to this kind of vertical line that we had in here. So this way of thinking is closely related to the idea of using the wedges in here. And yeah, then when you integrate these kind of conditional probability densities, you will be integrating with respect to the coordinate phi. And what was missing in my original question was actually the specification of how you should think of integrating this density. You can integrate over different x's, you can integrate over different phi's, and then you will get different answers. And yeah, you should avoid conditioning on events that have 0 probability, but you will be able to condition on specific values of x or specific values of y, specific values of phi. And if you do that, there will not be a paradox. So that's kind of the resolution. Yeah, before I show you a little bit of the calculations, do people have questions? Anything I should explain here? I think I should try to speed up a bit. I will not discuss with you all of the different details of the calculations because yeah, we are kind of out of time, but these are in the notes and I will show them briefly here. Yeah, by the way, as for the name of the paradox, what I described here was kind of my version of the so-called Borel-Kolmogorov paradox. If you go to Wikipedia, you can read about the Borel-Kolmogorov paradox. They used actually a sphere for the demonstration, but I thought it would be actually more pedagogical to think about a semicircle. So as for the resolution, I provided here calculations in 2 different coordinate systems. When you have time, you can take a look at that. So you can have these coordinates x and y that would be related to this way of thinking, and you would be able to specify the probability of some event A using these kind of integrals involving an indicator random variable for an event capital A. And you would be able to calculate the marginal PDFs. I guess I haven't really introduced this properly in here, but just quickly, you would be able to work with marginal PDFs, conditional PDFs, and then when you condition on x, on some specific value of x, you would find that the mean value of y is this precisely. If you go to the limit when x goes to 0, you get 1/2. So this will be the average height in this particular case. Yeah, by the way, as for the conditional PDFs, I will introduce them in a second, but I wanted to show you that a calculation like this is possible. So you will see that in the notes. And yeah, the other coordinate system that would be related to this way of thinking with the wedges. Yeah, with that coordinate system, you would have values of r and phi. This would be the probability of a certain event using some indicator function, indicator random variable for that particular event. And you would be able to work with the marginal PDF of phi, calculate the conditional PDF of the radius variable r if you are conditioning on a specific value of phi, and then you could calculate the mean value of r given this conditional distribution or using this conditional distribution. So if you calculate that, if you calculate this integral in here, you will get 2/3, so that's the alternative answer. And in this case, it's fine to condition on phi, it's fine to condition on x, but you have to be specific. You have to specify how you are going to do the conditioning, because you cannot just say you will condition on a set of probability 0. Yeah, maybe I can also include some of these calculations in the problem sets and so on. So that's a resolution of the paradox. And yeah, now that I think about it, I will have to go here and explain the individual concepts of joint PDF and marginal PDF and conditional PDF. You just saw them in the calculation, but for clarity. It may take some more time. I hope you don't mind staying. So for clarity, if you have a continuous distribution, say of 2 variables in here, you would be able to introduce this joint probability density function in here. This joint probability density function is plotted for some normal distribution corresponding to 2 variables. It's fairly analogous to what we had for discrete random variables. So I will go through this relatively quickly, but you should keep in mind that there's the paradox and you have to be careful about how you condition things. So we will have some joint PDF, that's the joint probability density function. That will be a function of x1 and x2 if we have 2 variables only. And I'm going to use little p in here. So hopefully this will not be confusing, even though for the discrete variables I used this little p to denote the joint probability mass function. Yeah, so keep this in mind, but if you understand what this p means, you will find that the formulas are actually pretty analogous. And yeah, I'm getting a question. So we cannot condition on specific points of a continuous space as they are 0 probability events, but we can condition on ranges in the continuous space. So definitely you can condition on ranges, that will be fine, as long as the particular range has some positive probability. But I'm saying actually one thing beyond that. I'm saying that it is okay to condition on specific value of a random variable. It's okay to condition, say, on x in this example. It's okay to consider conditional distribution on x. It's okay to consider conditional distribution when you condition on the value of phi, but there's like an extra piece of information. So when you use this conditional distribution, you have to specify which variable you conditioned on. So it's perfectly fine to condition on x equal to 0, and then you will have some meaningful probability density function in here. And it's perfectly fine to condition on phi equal to 0, and again, you will get some conditional distribution in here. But these two distributions are going to be distinct. You have to specify the function, and also you have to specify which variable you conditioned on. Yeah, so again, to recapitulate, you can specify conditional distributions, but you have to also include this piece of information, which is which variable you conditioned on. Then there is no paradox. But if you omit saying what you conditioned on, then you will not get some concept that is meaningful. So that's what I mean when I say you cannot condition on a set that has 0 probability. And yeah, a question. So coordinates implies the function we integrate. Yeah, you can think of it that way. That is, yeah, if you specify which coordinate or which variable you conditioned on, we will also know how we should take integrals if we want to consider different values of this random variable. So I think I agree with this statement. It's a little bit confusing, but yeah, hopefully it's clear right now. If you do provide this extra piece of information of what you conditioned on, then things are okay. There's no paradox. Now, interestingly, very few people are aware of that. Even people who use conditional distributions in their research or in their job, they may not be aware of this paradox. Anyway, as for the concepts that we would use for continuous random variables, so we will have this joint probability density function. You can have a marginal probability density function that you would obtain by integration, like this. And then we will have conditional PDFs. And well, in the end, for the conditional PDFs, we will get formulas like what we had previously for the conditional probability mass functions. So the conditional PDF of x1 given x2 is going to be this kind of ratio as long as the PDF of x2 is positive. But yeah, this is not going to be defined when the PDF is actually 0 in there. Now, how could you define this conditional PDF? I mentioned previously this long formula where we had the probability of x belonging to B expressed using a double sum. Well, you can replace those sums by integrals in here. And you can say that the PDF of x1 conditional on x2 is going to be a function such that the identity that you see in here is satisfied. That is, yeah, you require that this double integral that you have on the right-hand side, when evaluated, gives you the correct values for the probabilities of events B, or like the event of x belonging to B. So that's how we can sidestep the problem of dividing by 0, and yeah, these kind of specifications, they will work in the context of these integrals. So that's what we would have. Most of the time, you don't have to think too much about the paradox. You would use these joint distributions, marginal distributions, and conditional distributions. But of course, you have to keep in mind that you need to be specific about the variable that you conditioned on. And yeah, then one more thing that I wanted to include in today's meeting, and maybe it's getting a little bit too long. Yeah, for those of you who don't mind thinking about measure theory, I have some more complicated definition that would also be more general. So this would be a definition of conditional distributions if you have arbitrary random variables. So we will not be specific if the random variable that we conditioned on is discrete or continuous or something in between. We will have a definition that works in general. Now, yeah, some people told me that they would be interested in having some more detail on measure theory. If we do that, it would be some separate meeting. Maybe not everyone here will be interested in understanding the details of measure theory. But yeah, let me know if you would like to have a more detailed discussion, more detailed clarification of all of these measure theory concepts. I think it would make sense to schedule a separate meeting on that. Now, if you want to make things general, then you can do it in the following way. Let's say that we have some variable capital X and we want to condition on that. We want to condition on the values of this random variable X. And let's say that P tilde X, that's going to be the distribution of X. And then we would like to define this px, that's going to be our conditional distribution given x. That is, at this moment, it's going to be a candidate distribution corresponding to some specific value, little x. So that will be our notation. And we will have some consistency requirement in here. Maybe it's kind of obvious, but if you have this distribution px, or I guess you can say probability measure px, then according to this probability measure, it must be the case that capital X has the correct value, right? That is, according to this distribution that's conditioned on a specific value of little x, this event, x having that specific value, that event must have probability 1. Now there can be some exceptions, and I mentioned exceptions in here, but yeah, roughly speaking, if you conditioned on a specific value of little x, then according to this conditional distribution, capital X must have that value. Yeah, you can think of this x corresponding to different age groups, for example. Maybe you have population of people with different ages, and then you want to consider this probability measure that's specific to people who have a particular age. So let's say x is equal to 70, maybe 70 years old people. So in that case, the probability that the person has 70 years should be equal to 1, up to possible some little exceptions in here. So it's a consistency requirement. It's just something that we would like to have if we condition on a subpopulation that has specific age. Then there will be some technical requirement. So if you have this conditional distribution given x, or like conditional probability measure given x, then if you have some event, capital A, the probability measure of that event should be measurable. So you should be allowed to compute integrals. So the technical term here is that it's a Borel measurable function. Yeah, you can say that the pre-image has to be, the pre-image of any open set has to be a Borel set. Yeah, it's a technicality. Without this technicality, we would not be able to use the appropriate integrals. And this is kind of the main part of the definition. So the main requirement is that you can decompose the probability of some particular event A into contributions that correspond to different values of x. And you would kind of integrate it over different values of x. So for example, let's say that A corresponds to the event that the person has more than 150 centimeters, right? So if you have small kids, it's going to be unlikely, like if you have very young kids, it's going to be unlikely that they are above 150 centimeters tall. And then this probability is going to change over time. And then this P with subscript x, that's going to be the probability that the height is above 150 centimeters, given the specific age. So it's going to be close to 0 if you have a 4-year-old kid. It's going to be higher if you have someone older. And the integral that's written in here basically corresponds to summing up these individual conditional probabilities over the age distribution. So to compute the integral, you would consider all of the different age groups with the appropriate densities, right? So there will be maybe quite many people who are 10 years old, and there will be few people who are over 100, or maybe who are 110 years old, right? So this kind of consideration of the different proportions in the population, that's included in the definition of this integral. And yeah, to summarize this formula in here, you require that the probabilities of these different events A can be decomposed in this form using the conditional distribution and using the distribution of the variable that you conditioned on. It's analogous to what we had before, like these decompositions using sums and integrals. So here it's kind of written in a more general form. And yeah, maybe just one quick comment on the measures for random variables. 2 weeks ago, we talked about this counting measure and the Lebesgue measure. So I may want to elaborate on it a little bit, but that will be the last point. So if you have some particular event, capital A, then maybe the probability measure that you consider can be decomposed into a Lebesgue part and counting measure part. And to be specific, if you have a discrete random variable, then there would be no Lebesgue part. There would be like no continuous part of this right-hand side. And then, yeah, if you have a discrete random variable, this little p is going to be 0. And the distribution can be written using the counting measure. And as for continuous distributions, you would not have the counting measure part, you would just have the Lebesgue measure part. If you have mixed random variables, then they can have both, right? So yeah, you can think about the wage distribution in society, something that we discussed some time ago. You may have the counting measure part, maybe people receiving exactly the minimum wage, and then you would have the Lebesgue measure part that would correspond to the rest of the distribution. So if you have a mixed random variable, like a mix between continuous and discrete, you could write this distribution of x using the Lebesgue measure and counting measure. And yeah, the notation here looks kind of complicated and fancy, but really what this is supposed to mean is on the right-hand side, having an integral and having a sum. You would be integrating over the continuous parts of the distribution. You would be summing over the discrete parts of the distribution. Now, this was for those of you who may be interested in measure theory. I wanted to elaborate on it a little bit to give you a sense of what this kind of integral that I had in here can involve. But yeah, long story short, in the case of discrete random variables, you will be summing. In the case of continuous random variables, you would be integrating. Yeah, so if people are interested in measure theory, we can devote one of the future sessions to that. I understand that probably from my exposition, if you see measure theory for the first time, it may seem confusing. I would be happy to clarify in that case. Yeah, if this is too complicated, then don't worry. Definitely, it's sufficient for you for practical purposes, for the main practical purposes, to understand what happens to these conditional distributions when you have discrete or continuous random variables. And yeah, keep in mind that you cannot condition on sets of measure 0. All right, yeah, so the session was way longer than I expected, but it's great you were able to stay until now. And as for the next topic, we should be talking about estimators, and we should be talking about convergence of random variables, asymptotic theory, and stuff like that. So that's something that's definitely very important if you then want to do some hypothesis testing, if you want to work with regressions, and so on. All right, so this concludes this set of 3 lectures on the dependence of random variables. Yeah, it's great you were able to join. Thanks a lot, and see you next time.